So there are two companies, Solaris, I'm from Solaris, and also Transvalor. So Solaris is a company that provides engineering and consulting service in the photovoltaic industry in many subjects. So ranging from solar resource characterization, forecasts, design and development of large scale PV plants and other services. It was founded in 2008, and we are located in southern France. Transvalor is also in the same area in southern France, and it's a company that provides solar and weather resource for site assessments and forecasting. So we are on a similar discipline. However, Transvalor takes advantage of satellite imagery. They supply the SODA web service platform that gives access to helioclim data. So this is a database that is owned and provided by Transvalor. They are also official provider of the CAMS radiation service. And we both work very closely with the Center OIE from Mines Paris, which is a research center from French University on observations, impacts, and energy. So now talking about these projects, the project aims to give some service to the photovoltaic forecasting, of course, especially in the range of a few hours ahead forecasts. Of course, there are already many algorithms to provide this kind of forecast. However, we think there is some room for improvements in these forecasts. The main one being that this forecast already use satellite pictures and satellite images to provide the expected power. However, they typically use advective approaches, which means that based on a series of images, they try to track the clouds and derive the motion vectors of the cloud to provide an estimation of the next satellite picture. Now, there are powerful algorithms to do this, but they rely on some assumptions that are quite restrictive in the case of cloud forecasting. The main assumptions being constancy of the lightning and also no formation of clouds. And also there is an implied restriction of this algorithm that since it uses only two pictures, it is difficult to derive rotating movement that can frequently happen in meteorology. So what we propose regarding the technical parts is to provide an algorithm that does kind of the same thing, but using deep learning techniques, such as generative adversarial neural networks. That's what we expect to develop in the project. So these are machine learning techniques that are theoretically able to leverage some context information from the satellite pictures. What I mean is they will not be restricted to only physically derive the motion vectors and propagate them. They can guess some meteorological context from the pictures, and we can also augment the input and give them explicit conditional meteorological features, such as forecast from or observation from meteorology providers. And all of this can help the algorithm understanding the context and theoretically derive better estimation for the next satellites, because they can understand that in this kind of context, it is expected that some clouds could appear, or that we are in a typical situation where clouds have a certain type of movement, and they can identify all of this by comparing the features to past data and propagating them. So effectively, this will increase further the horizon range in which we can use satellite information from actually currently a few hours to maybe 6-7 hours if the results follow. Now, the development of the project will be in two phases. The first one will be, of course, the development of the algorithms and the training of the model, since they are models that require some training periods. For this, we expect to use Transvalor hardware, since we are already possess some hardware that allows this kind of calculations. And also, since Transvalor is a provider of Copernicus data, they already have a large part of the data that we expect to use in this project. And so it is a good idea in the development phase to have the calculation made as close as possible to the data to facilitate all the back and forth that can happen during the development phases between data, models, and training. Now, in the second phase, once the model is validated, we expect two things. First thing is to augment their capacity by providing them exogenous data coming from numerical weather forecast providers or meteorological observations. All this data will be coming from, of course, other Copernicus services. So we have to link this first algorithm with Copernicus, and also we want to host the algorithm on maybe a DIAS such as QDIAS or Wikio, so that every potential user of the forecast can access them. So in this phase, we do not require as much calculation power, since training is the most difficult part that requires the most calculation. So calculations can also be done directly on the DIAS using hardware from the Copernicus environment. Now, a few words now to conclude about who are these forecasts useful for. Mainly, we expect it to be useful for managers of isolated systems, such as off-grid power sites, or maybe transmission system operators of island power networks, and the likes. Because, of course, these forecasts in the few hours are more requested for stability of electrical power grids rather than energy trading or things like this, because energy trading requires forecast for the next day. In the few hours range, it's mostly, yes, for operators of power systems. So we expect that they will benefit greatly from the developments that we propose in this project.